Let's take a couple minutes and see if we can't finish the last two questions from Momentum Homework 2. The last two questions are as follows. Let's do number 4 out of 5 here. It says a quarterback of mass 75 kilograms is running toward the end zone at 6 meters per second. A linebacker, mass of 100 kilograms, runs toward the quarterback. He's running at 4.5 meters per second. They collide at the 2-yard line. Does the quarterback score? Right? I understand that sports references aside, this one might be a little challenging, but let's see if we can't make a good picture here. So here is the quarterback, okay? We're going to put the football in his arm here. Okay. He's carrying the football and he is running this direction. So those little motion lines. So let's put the stats on here. So he's 75 kilograms and he's running, in this case we have him running toward the right at 6 meters per second. He's running toward the linebacker who's attempting to keep him from scoring. Okay? Attempting to keep him from scoring. So he's running this way, and his stats are the fact that he is a 100 kilograms, and he's running at 4.5 meters per second. Now, if you're paying close attention, you know this is a problem about momentum. And so this guy's running to the right, so his speed is 6 and his velocity is positive 6. This guy's running to the left, his speed is 4.5, but his velocity is negative 4.5 because he's moving to the left. That's probably going to be important. We know that they're going to collide at the 2-yard line. Okay, they're going to collide at the 2-yard line. So let's see if we can draw a picture for that. He's going to collide head on with this guy. And we want to know, does he score? So if the 2-yard line is right here, okay, if the 2-yard line is right here, does the quarterback make it over to the goal line, which is over here? That's the question. And so we got to figure out, is there a way for us to know? Well, what we're trying to say here is that when we go to calculate the motion quantities before and the motion quantities after, if they hit and collide, but their velocity is to the right, then he's going to score. If their velocity is to the left, he's not going to score. And if their velocity is 0, they're not going to score. He's not going to score. So we got to go and we got to calculate it, and then we're going to go and calculate the energies and see how that works also. So let's start with the energy bar charts. All right, we know what these look like. In our system is the, quarterback. So the QB for quarterback, and then the linebacker. Those are the guys in our system. And again, we have gravitational, kinetic, and elastic. Over here, gravitational, kinetic, and elastic. So that looks pretty cool there. And then down here, we're going to go to calculate our motion, our momentum bar charts. Now that we have a fully formed momentum concept, or at least a partially formed momentum concept, we can call it what it is. We're going to hold off on doing the energies now because we're going to go and calculate the kinetic energies in a minute. Let's do the momentums down here and see if we can't figure out what's going on. So when I go to draw the linebacker, one thing I notice is that he is much more massive, right? He's 100. So I'm going to draw him a full 100 here. And then what about the quarterback? He is 75. So that's 3/4, so I'm going to draw them like that. So there's their masses. Now what do I know about their velocities? The quarterback is running to the right at 6. So if I call this 6, what do I know about this guy? He's running to the left, so his velocities are going to be left, but he's only running at 4.5. So let's put the numbers on here. This guy is 75, and he's running at 6. That's a positive 6. This guy is 100, and he's running at negative 4.5. Well, if I do the math to find the areas, this one's easy. This is negative 450. Well, what's 6 times 75? It's positive 450. What I like about this is that we're starting to get a sense of what's happening. I'm going to go and do the masses over here again. So here's the total mass for this guy. Here's the total mass for this guy. But what do I notice about the momentum? Total momentum on this side is 450 plus a negative 450. That's a total momentum of 0. And if that momentum is 0, we know that the total momentum on the left has to be equal to the total momentum on the right. What does that mean? That means that neither guy ends up moving. So momentum equals 0, which means both velocities have to be 0. So the moral of the story is, does he score? And the answer is no, because the linebacker had just as much momentum, and so the momentums add to 0, and they hit and stick and stop at the 2-yard line, which I think is really interesting. The rule is, the guy with more momentum wins the collision. The guy with more momentum wins the collision. That's an important idea. All right, so let's talk about what happened with the energies here. If I calculate the energy of this guy here, 1/2 mv squared. 1/2, his mass is 75, and his speed is 6 squared. So what is his kinetic energy? Sorry about that, I have to calculate it. So his kinetic energy is 1,350 joules. All right, that's good enough for him. Let's see about the linebacker, the red guy. His kinetic energy is going to be 1/2. His mass is 100, and his speed, now his velocity is negative 4.5, but we're going to square it, so it's not going to end up mattering. His kinetic energy is 1012.5 joules. So they almost have identical kinetic energies here. The guy who's faster has a little bit more. And so it's hard for us to draw these in terms of boxes. Now I know that this guy has, the blue guy has a little bit more kinetic energy. So I'm going to draw his box just a slight bit more. I mean, it's only 300 more out of 1,000, so it's not a ton more. Okay, that might not be to scale, but it gives you a sense of what's going on there. And then, what happens? Over here, what we realize is they hit, stick, and stop. There's no kinetic energy, there's no gravitational, there's no elastic. Where'd all the energy go? During the collision, it was all released out of the system as some sort of thermal energy or sound energy or whatever. And what we have is we have a combination of those two energies right there that have left the system. And I think that's a pretty full picture. All right, let's do the last one. Okay, this one talks about bumper cars. Okay, this one talks about bumper cars. The bumper cars at Cedar Point are a good model of bouncy collisions. An evil bully in a blue bumper car. Total mass 270 kilograms streaks toward a red bumper car sitting at rest. All right, so let's try. I don't know how to draw bumper cars, but let's just try anyway. I feel like a bumper car. It looks somehow like a shoe. Well, in this case, it looks like a fish. Maybe it's slopey down in the front. Still looks like a fish. All right. There's a red bumper car over here, just sitting there, minding his own business. Sitting at rest, okay? Now, interestingly enough, it says that the mass of the red one is only 230 kilograms. The mass of the blue one is 270 kilograms. This guy's moving to the right at 5 meters per second. And this guy's at rest. So this is the initial state. The final state says that after the collision, this guy's moving forward, but now much more slowly. And this guy has moved off much faster. It says his new speed, he slowed all the way down to 0.4 meters per second. And we would like to know what the speed of this guy is. No problem. I'm also interested in what the energy situation is. But now we have a good diagram, so let's draw the LOLs for this. Gravitational, kinetic, and elastic. So over here, gravitational, kinetic, and elastic. We got the red bumper car and the blue bumper car. Okay. I think to understand this, though, what we're going to need to do is we're going to need to do the momentum first. And if we can do the momentum first, I think that's going to give us a better sense of what's happening here. All right, so we got our diagrams. So let's see what we got here. Now, we have the blue one, it's 270. Now this one's 270, 230. These are almost identical. Okay, so we'll make this one 270. And we'll make this one 230. We'll make it slightly less, almost like you couldn't even tell. Same thing over here. 270 and 230. Like you can't even tell. Because they're very close to one another. But the initial situation says this guy's moving to the right at 5 meters per second. And this guy's at rest. Afterward, he's only moving to the right at like 0.4 meters per second. So this is 5 meters per second, 270. This is 0.4 meters per second, 270. And we got to figure out how fast this one is going. Now I know I'm not going to put a thing on here because I don't know how fast it's going, and I know the areas have to match. So let's do a little quick math on this and see if we can't figure out what the math is on this. So I have 270 times 5 meters per second. So it's 1350. So the total momentum here is 1350. That's the total on the side, which means that since you have 1350 on one side, you need 1350 on the other side. What we have is this one right here. This area inside here is only 108. So the total has to be 1350, and so what are we left with? That means we're left with, the area for this one has to be 1242. Well, the area has to be 1242, and we know that the mass of this one is 230. What does the velocity have to be? Well, it turns out the velocity is 5.4 meters per second, because 5.4 times 230 is 1242. So it turns out, after the collision, 5.4 meters per second. This is a great idea here because, again, the total area over here has to match the total area over here, and visually it works. This is shorter than this one, but it's a little bit longer. You have to add these two areas together to get this area. I think the whole thing makes a ton of sense. Let's do the energy calculations real quick. Over here, only one guy is moving. So if I go to calculate his kinetic energy, it's 1/2 mv squared. The mass is 270, and he's moving at 5 meters per second. Give me a second to calculate. So 3375 joules. All right, so we're going to have some large amount of energy here. Again, with these big numbers, it's hard to break them up into boxes. But we know this is a total of 3375. Let's calculate the kinetic energies over here of each of these. This is 1/2 mv squared, 270 times 0.4 squared. This is a small amount. This is only 21.6 joules. And what about the red one? For the red guy, his mass is 230 and his speed is 5.4 squared. So this is 3,353.4. Now, what's interesting about this is I'm noticing something really interesting about this. This is a little bit smaller than that, but how much smaller is it? Is it 21.6 smaller? It turns out it totally is, because when you have these bouncy collisions, all the energy stays the same before and after. We call that the law of conservation of energy. And so as long as your collision is bouncy, you don't lose any energy to the surroundings. Therefore, the heights here are the same, but you have most of the energy is in the red one and a little bit left in the blue one. I think that's good.